Hello Internet, today we are going to be exploring dynamic programming. So in this episode we're going to be looking at the change making problem. So it's a pretty classic problem of mathematics. And so the idea is, given some amount of change you need to make, what is the least number of coins required in order to make that? So we're going to be using American currencies, so that means pennies, nickels, dimes, and quarters. So 1, 5, 10, and 25-cent pieces. And so given any number, say 79 cents, for example, you need the best way to make change for that. So there's a number of solutions for this. We're going to look at two of them. The first one we're going to look at is actually just the naive solution, sort of the greedy algorithm, which is just going to say, can we put a quarter in there? And if so, let's return that. That isn't actually the optimal solution, and we'll look into that with our next version, which is going to be actually using dynamic programming, which is the idea of kind of breaking a problem down into its component parts and then solving each of those parts iteratively in sort of a sequence in order to build up to your final solution. So I figure let's get started and look into how to solve this the easy way. So what's the best way to do this? Probably with a for loop. Is it with a for loop? Sure. So for each int between I equals, let's say 1 and I is less than 100. So from 1 to 99, we want to iterate over every element in there. And so the idea here is we're just going to iterate over all the possible combinations, all the combinations we really care about, and try to make something for that. And so each of these is going to have a console write line, and we're just going to print out our calculate change. And that's just going to, for our purposes, we can actually probably just return a string. This isn't going to be particularly pretty, I don't imagine, but we're going to see what happens here. And so we want to calculate change for I cents. And so theoretically, if I stop clicking the wrong thing, we can generate this method here. This is thinking it's returning a boolean. Let's return a string instead. And we'll accept the change amount that we want to make. And then there's going to be a set number of pennies, of nickels. Did I spell that right? I feel like that's not right. Dimes, and then of quarters. So there's the 4 coins that you can possibly have. And so pennies, obviously 1 cent, nickels 5, dimes 10, and quarters 25. That's just some of the people watching may not be from America or may not be familiar with the currency, so that's what we're doing. This algorithms, both of these should work for any amount of money. So if you have a different set of currency, actually, let's configure it this way. This will be better. So let's do a dictionary. Dictionary makes sense. And we are going to have the value, which is going to be an int, and something else. Actually, just the string works, doesn't it? Yes. So given a string and a value, we now have our coin types. So if we're just doing basic American currency, that's going to be a dictionary of our string and our integer, like so. And we'll just make a list. So this is the shorthand for a dictionary in here. It may not like that because we didn't give it a name. That's fine. So we're going to do pennies, and that's going to be 1. And then we're going to do nickels. That will be 5. And we can just kind of continue down this line. Right. So now that we have this dictionary here of all of our currency types, we can actually just use this instead of this thing to calculate all of the denominations. So what we want is we want a dictionary that is going to store a string and then an int, and this int is actually going to be the number of each of those coins that we're going to return. So it's going to store each of these values plus the actual result we want. So we have our dictionary, and this is going to be our resulting change amounts, which is a very long name, but that's fine. We've got IntelliSense to type that out for us. We don't need to type it. So we can do that. And then just for clarity, I can actually remove that, change that to a var, which is just going to automatically infer the type from this. So it's not any different. It just makes it easier. And that way, if we ever need to change this, we don't need to worry about changing it in two places. Actually, we can do that up here too. Ooh, I lied. Never mind. Can't do that there. That can only be done inside of there. Yes. That doesn't seem right. Hold on. Var test equals 0. What's the error here? Can only be appear within a local variable declaration or in script code. Ah, so that is true. Okay. So you can't just declare a variable as a class level variable. Well, that's news. Anyway, we have this. The only other thing we need to do before we actually start solving this is actually take... What's the best way to do it? Sorry. Thinking. Let's actually iterate over all of the coins, or for each coin in the coins. And we want to order it by our KV, which will be our key value pair. And we want to order it by our key value pair, and we want to order it by the value, actually, which I believe should order us down. It shouldn't change anything. But if we order it by descending, suddenly now it should work. So we should get our largest denominations first, and then we should get our next value next. So the important part here is now we can now do int coin amount and set that equal to 0. Why doesn't it like any of this? This is not static, so we cannot access it. I'm going to make it static here. Probably the better option is actually to pass it in. But we're not going to do that because then I just need to access it here anyway. So that normally if we were writing this, we'd break it off into component parts and this would be separate from our main function. We're not doing that because we're kind of exploring the algorithm, not so much this. So this is sort of a little bit thrown together, I guess. But the general idea is don't make things static if they don't need to be. It's just a waste, especially public static like this. That's not a great idea, but we can save ourselves a little bit if we declare it read only. And so that way nobody can come back and change this. It doesn't really protect us because they can actually still remove things from this because it's just a reference. So they can just still change the actual reference values underneath it. Nothing's stopping that. But this will at least prevent people from replacing this coins reference with something else. And that's as good as we can do. Anyway, that was kind of a tangent, but we're going to work with it. So while our change is greater than 0, or greater than our coin.value, so the amount of value each coin represents. So if we're doing a quarter, as long as we're greater than 25 cents, greater than or equal to actually, then we can actually use that coin amount, or we can use that coin. So we'll change the coin amount and increment that. So we'll use one more of those coins, and then we will do something else. reduce our change. So subtract our coin's value from the change we're trying to calculate. And so by doing this, we're slowly decreasing the amount of change left to calculate and just adding more and more of this. And then finally, we want to add our resulting change amounts. And we're going to add our coin's key and then the coin amount. So this is going to give us the resulting number of coins for each key that need to be returned for this. And then we just need to return a string of that, which I believe can be done by just doing toString on a dictionary. I think this will print out something useful for us. There's one way to find out. I'm going to stick a read line right at the end so we don't exit our program immediately and just lose our output, because that kind of defeats the point. And then let's see what we get. So we're expecting to see not that. This is less helpful. We got our 100 lines, but it's all just the object types, which isn't really useful to us. So we are going to need to do something else. Is there no way? Sorry, this is going to be totally random, but I kind of want a way to print this without having to do all sorts of crazy stuff. I think I found something I like more in Java than in C#. So in Java, all maps, so your heaps and your binary tree, not your binary trees, your heaps and your dictionaries and that kind of stuff, all of that has an abstract implementation that defines that all of their toStrings will actually return a representation of that map. That's not apparently the case in C#, which is too bad. It would have made our job easier, but that's no problem. We can work through that. So what we need some way to convert this into a string, which we can do the horrible way or the better way. We'll do it the better-ish way. We'll do a stringify function, mostly because I like that name. I think it's a fun name. I'm going to say I spelled that wrong, but I don't think it's a word, so I don't think I can spell it wrong. So all this is going to do is it's going to stringify our resulting change amounts. So we return a string from our dictionary, which relatively simple. So all we need is a string builder. So we put our builder there and assign a new one to it. And so a string builder is just going to be, it builds strings. That's the easiest way to think about it. But the difference is if you just keep appending to a string, strings are immutable types, which means every time you add onto a string, you're taking both of those two strings and you're discarding them because you no longer theoretically need them. And now you're making a third string. And then if you keep adding onto it, each of those intermediate strings are still getting generated. They're just getting immediately garbage collected, which is just a pain and wastes a bunch of memory and is super slow. So this way a string builder doesn't do that. It avoids that problem. So it's going to be a lot faster if you're building strings like we are. So that's what we're going to do. So the way this works is we do a for each on our coin amount in our resulting change amounts. And then all we need to do is do a builder dot append, and then we just append our coin amounts, key, and the value. So we have that and something else. Yeah. So we can just append a few things. There's a format option. I'm not going to use that because it's just more work, honestly. And I'm not sure it gives us any it would make this cleaner, but it wouldn't make it any faster, I don't think. I'd need to confirm that, but anyway. So all this should do is, one sec, print out the coin amounts and then the value of the number of coins associated with each of those. And then put a bunch of spaces between them all because that's a thing we do. Just a space actually, because that was excessive. So let's do a toString here, and now we actually can return it. So that, theoretically now we'll get better values. Yay. And so that's really hard to see, but you can see, actually, one sec. There is a better way to do this. We're going to print I plus, no, I said don't use plus. We're going to use plus. So we're going to do that. And the reason we're doing just this I plus is so that we can actually capture the number we're actually using. And so this way we can actually see what we're doing. So for 99 cents, we're going to do 3/4, 2 dimes, which gets us up to 95 cents, and then 4 pennies. So that's a total of 9 coins. And so our goal is going to be to actually reduce this so that we use less coins for these solutions. So how do we do that? Like I said, the idea of dynamic programming is kind of to divide a problem up into its subsequent parts and then try to solve it from there. And so a lot of times, instead of doing it one direction, you do it the opposite direction. So like right now, what we're doing is we are taking a value and then we're going down towards 0. With dynamic programming, the way you solve this problem is you actually build up towards that number. So instead of doing this, what we're going to be working on is we're actually going to be building up. So we're going to start at 1, and then we're going to keep adding up from there. So the way we get to our solutions is going to be a little bit different. I'm actually going to keep these things here because I think they'll probably come in handy. And then we'll do a write line, I plus that plus R, calculate change dynamic, which is going to use our dynamic programming version. And so the idea here is normally you'd start at, say you want to do 6. So what you would do is you would look at 6, and then you'd count back. And so what we just did is we said, oh, we can put a nickel in there and we can put a penny in there. So we did, and that sort of worked. Well, it did work. But what dynamic programming is saying is it's saying we need 6, and here are the denominations we can do. Looking back from that 6, what are the values we could use, and what were the solutions for that? And then if we take that plus 1, because we're adding 1 extra coin, what's the best solution? So what's a good example? Say 25. There's a ton of ways to do 25. So what you could do is you could do a quarter, obviously. You could do 5 nickels. You could do 2 dimes and a nickel, and so forth. And what dynamic programming does is it takes each of those into consideration and says, what was the best solution at 24? So if we got to 24 coins, or 24 cents, if we add a penny to get this change, because that will obviously get 25 cents, is that the best solution? And so then you look at it and say, if we add a quarter, is that the best solution? Because that's just 1 coin. If we add a nickel, for example, and look back at 20, is that the best solution? And so it looks at it that way. So that may have been a bit confusing, but we're gonna get there. So this should look almost identical, and we're still going to return a string. The only difference is I'm going to want actually a array of dictionaries. So what we want to do is we want to actually store our old solutions like this. That's not how you do that. Optimal change, I guess, was what we'll call this. And so this will just be a new list. And it's going to be a list of our optimal solutions for that amount. Oops. So all that's going to do is it's just going to be a place to actually store that. So this algorithm does incur a bit of space complexity that you wouldn't have with this normal calculate change. So you don't normally, this isn't requiring you to really store that much. You do the calculation and then you're done. The problem is the calculation isn't actually correct. So the best way to do that is actually to store optimal changes, and then based on those we can actually figure out what to actually do. So now that I've rambled on and on and on and on and on, let's actually solve this. So we want our optimal change to be, well, first we actually want a new dictionary, and this is going to look gross. Oh no, we don't want to do that. Shoot. Sorry, my bad. We actually want to do something like this for this stuff. We want all of that exactly the same as what we had. The only difference is we are not actually going to have this while loop. That is going away. It's not needed. And so for each variable of the coin, ordered by descending, yada yada yada. So if we start at 0, we need to actually consider 0. So we're iterating over all of our coins. If we get to 0, then we're done. That's the solution we really care about. So what's the best thing to do here? Sorry, I'm considering that this may have been the wrong solution, but we're going with it anyway. I'm running into issues. I don't like the dictionary bit because that makes it hard to actually calculate the total number of coins, because you have to iterate over this dictionary and then add up those integers. I don't particularly like that, but I don't think there's anything we can do to solve that. So let's do resulting change amounts is going to be equal to this. We don't really care what the order is. We just need to iterate over the coins. We don't need to enforce an order because we're actually going to try all of them. So the coin amount is going to be equal to calculate coin amount, and we're going to pass in our resulting change amounts, I think. Yes. And so all this is going to do is it's actually just going to calculate the total amount of coins at any particular point. And we're going to actually discard anything that falls into 0 or below, or anything that falls below 0. Because you can't make, if you return, what that's going to mean, rather, is if you actually return, give like a quarter, for example, for 15 cents. That gets you -10 for the change. That's not really valid. So we're going to ignore those kind of solutions. Why was I just talking about that? We're not to that point yet. I feel like I've been talking too much today. I spent all of the day at work discussing various things and giving presentations and all of that fun stuff. And now I get to talk to you guys, which is fun. But it's a lot of talking, and I'm not really used to it. Regardless, what is going on? There we go. So we need a coin amount, which is going to be equal to an integer of coin amount, or coin count rather. And that's going to be for each coin in our resulting change amounts. We want to add the coin's value to our coin count, which I believe we could do with link, but we are not going to because this is far easier to understand than calculating a sum by deconstructing dictionaries. You can do that, and I have done that, but don't. You can do it if you want. I'm just not going to. The code doesn't look nice. Anyway, another tangent. We're going on too many tangents. Regardless, we have this. This algorithm is just going to iterate over our dictionary and add our coin values up, and then we're just going to use those as our result. So all this does is really get the total sum of coins in our change amount. And remember, we're not going for like the most number of like quarters, for example. We're going for the least number of coins you can return, which can be different. So let's see, we have our resulting change amounts, and we want to add our coin key. What we want to do is iterate over each coin that is in our system. So we have 4, and we want to take our current change and subtract that. So int target amount is going to be equal to, actually we can call this the index. The target index is going to be equal to our change minus our coin dot value. And so this is going to get the actual index in our previous optimal change. That was the solution there. And so theoretically, say we're on a dime, we'd subtract 10, and then say if we're above 0, or if we're greater than or equal to 0, whatever solution is at that position in our array, that was the best solution for that number. And so if we add a single coin to that, that's the solution for this number. So that's a potential solution. And then we get each of those for each coin type, and then we choose the best one. So our target index is equal to that, and then our coin amount is going to be equal to our calculate coin count of the optimal change, where the optimal change is equal to our target index. Right. And then this plus 1 is going to be equal to our best solution. So normally when you do this, you don't necessarily need to actually track the coins because you can actually just solve for that once you have it. But we're going to actually do it because why not? The reason I say that is because if you know the way you got to this solution, like if we know we used the -10 index, we know we used a dime. We don't need to actually store that we used a dime because we used 10 units back, which can only mean we used a dime. But that, I don't know if we need to actually skip that bit. Let's just add it. So we calculate the coin amount, got it, and then with our change equal to the optimal change of target index. What the heck? It's not static. Now it is. Problem solved. And now we're using 2 changes. This is not going well. So our optimal change is going to be equal to the temp change, which is going to be our temporary change amount for this specific solution. So our temporary change amount is equal to our optimal change. And then we want to do our temp change dot. And we want to actually store the value here. So we want an integer of our value equal to the temp change. And we want to actually get our coin key because these are going to match. And we want to actually add just one for our current coin. Then we want to replace it. So a temp change dot, does it have a replace? No. Remove our coin dot key, and then temp change dot add our coin dot key and our value. And so this will just add in our new incremented value for that amount and then save it. So if it's the best, then we want to swap it out with the resulting change amounts, which means the resulting change amounts becomes our temporary change, like so. And then finally, we just need to save this back into our array, which all of this, I'm sure, sounds way too complicated, but it actually will make sense, hopefully, once we get there. I'll kind of walk through it once we get a little bit further, because I'm kind of hacking this together as we go, because like always, I didn't actually plan this out. It's just sort of coming and going. So what we want is we want our optimal change, and I'm actually going to make this an array. And the reason we're going to make it an array is because it's far easier to actually index into this. There. So then we want to just store our optimal change at our change position as our resulting change amounts. So we're just saving things back into that array as we get them. So this only works if you start at the first one and go build up. If you try to start at the top and trickle down, this isn't going to work as well. You can make it work if you try to, say, calculate something below it. You can actually implement it so that it automatically calculates that one, but we don't necessarily need or want to do that. Since we're already starting at 1 and building up, we don't gain anything from not doing it. So the only thing we have to consider here is if the target index is less than or equal, well, if it's less than 0, then it's not a viable solution because we'd be beneath where we needed to be. And so if that's the case, then we just skip that. That solution is cast out. We can't use it. So I think that works. The only other thing we do need to do is initialize that initial value with a empty dictionary, which is going to be, how do we want to do this? We have a dictionary array, so we need our 0th dictionary entry. And that's because we're actually going to be looking that up when if we try to make 25 cents and we actually use a quarter, we're going to try to look up that 25th element or that 0th element. And we're not actually calculating that in any way because it's just a default value. So I think we should just be able to create an empty dictionary like this. And it should work. Oh, it's 100 long array. We need 100 element. Let's not do that. Let's just do an optimal change 0 is equal to a new dictionary. Done. It's not ideal, but it works. Right, so we have this. Now let's actually annotate this a little bit. So we're going to do our default, I guess. That's as good of a name as any. And then a dynamic. That's convenient that they have the same number of letters. Wasn't even planning that. Cool. So, theoretically, our default and our dynamic, we should see our dynamic actually have lower coin amounts than the other one. And so, what we can do is throw a little bar here. Again, string concatenations are bad. Use a StringBuilder, or in this case, use a string format. I'm just doing this because we're kind of riffing on this one idea, and it doesn't make much sense to actually do anything else. So what we need is we need to calculate the coin amount of our calculated change, which is going to be change default equal to our calculate change of I, and our change dynamic equal to our calculate change of I as well. Dynamic calculate change, there we go. We can swap this out with our change dynamic, and this out with our change default, which is, I guess, greedy would be a better name for that. Does it work? No, doesn't have the same number of letters. We're sticking with default. Just keep in mind that's actually a greedy algorithm. Not default doesn't really make much sense, but it does have the correct number of letters, which is almost as good. I should never be allowed to touch software. Anyway, we're going to calculate the coin amounts in each of those. So we have our default and our dynamic changes. And it doesn't seem to like that. String of ints, string of ints. Oh, it returns a string. That's less useful. Unless it returns a dictionary. Huzzah! Of a string of ints. Sure. Or of a, yes, a dictionary with strings and ints, and a dictionary with strings and ints. So everything's going to be the same. We're just not stringifying it in these functions. And this is actually probably a better solution because that's kind of a weird side effect to string your results. So now we aren't, which is good, I guess. Stringify, yes, awesome. And then all we need is to also stringify our dynamic change. Ooh, it really did not like whatever I did. Calculate change dynamic. I must be missing something. A namespace cannot contain members or fields? Methods or fields? I am definitely missing something. What did I do? Oh. An extra parenthesis. That totally messed up everything. But anyway, it's fine now. So what we can do now is actually compare the difference between our defaults and our dynamics. One last thing I'm going to do is write out our default like so. And now theoretically, this is probably going to blow up. But I'm going to run it and see what happens. We don't get a exception. Key not found. I expected as much. Did I expect as much? Yes. We are looking for pennies, which does not exist because our string did not create it, which is fantastic. Oops. So the one thing we skipped is when we created this optimal change of 0 at 0, we actually do need to initialize this with all of the funness of this. So I'll be right back. So what we needed to do is actually initialize our dictionary so it had these, because we were actually trying to look them up and it wasn't finding them at our 0th index. So by doing this and actually saying each of these is at 0, we're able to actually more or less initialize our 0 point to 0. So we should be able to do this. Oh, geez. Oh, I remember. I know what we did wrong. We completely forgot. Yeah, so oops. So we forgot to actually take the optimal solution, and we're just taking all the solutions. That's not correct. So we need to actually filter this based on our optimal change, or not our optimal change, our coin amount. So if the coin amount is less than or is greater than the current best exchange, I guess we'll say, then we'll continue, which will just skip over this one. And so what we need is a current best exchange, which is going to be equal to our int 32 max value initially, and otherwise our current best exchange is going to be equal to our coin amount. Ooh. There we go. And it doesn't matter that this is actually below our thing. So this is only testing what is the least number of coins already in a previous solution, and then take that and add whatever coin we need to get to the next best. So by starting at the max value, we're saying the current best solution uses an infinite number of coins, which isn't true. But what it does is it forces it to automatically pick the first solution and then continue to iterate over each of those. And so as it does that, it will pick, obviously the first solution that comes will automatically be picked. And then as better solutions come by, those will be selected instead. And if they happen to be worse, this will cause them to be skipped. So we should be able to start this now, and it's still wrong. It's only picking pennies. I think we may have told it to look for the wrong thing. If our coin amount is greater than the current best exchange. Oh wait, hold on. I get it. So we're taking this optimal change here, and we're actually copying it. We're copying the reference to it. This is wrong, because what this is actually doing is it's going to keep the reference. It's going to continue to be a reference to itself, which we don't want to happen. Because it's a reference value, even though we're assigning it to different spots in that array, it's going to have the same reference. So all we did is we assigned the entire array to have the same reference to the same object. So we filled our entire array with the same solution, which isn't right. So we need to duplicate this in some way, which is going to mean probably, yeah, there's no, what's the best way to do this? Copy and increment? Sure. Temp change equals copy and increment. And we're going to copy our optimal change at the target index. And we're going to increment our coin.key. And all we need to do then is assign our temporary change to that, like so. So then all we need to do is implement this, which is just going to copy our dictionary, like so. And so for each, well, actually we need a new dictionary, so we'll do that. Our new copy is going to be a new dictionary with type string and int. And we can just leave it like so. Actually, does it have copy constructor? It does. Why aren't we using that? We don't need this. Ignore me. I'm insane. I'm going to undo all of this. One sec. There we go. And we can actually bring all of this stuff back too. There we go. So all we need to do is just do a new dictionary like this and use the copy constructor. So we just copy, copy this. And so a copy constructor is just going to take in a reference to the same type of object and create a new copy of it, which is what we're doing here. And then we're just going to continue to use our temporary change to replace that value. So now that we have that, we should get better values. You'll see a lot of them are going to appear the same, but we should see some differences if I did this correctly. If I had been smart, I would have looked up ones that would have been different. They all appear to be the same. The solutions are different. So you can see for 71, our dynamic algorithm chose 2 quarters, 2 dimes, and a penny. And actually, so did our default. They're just swapped. Well, that's interesting. They shouldn't all be the same. If they are, I did something wrong. I think I did something wrong. Well then. Oops. Yeah, our solutions are identical, which does not make sense. That makes me think I did something horribly wrong. So how do we solve this? Calculate our dynamic change. One sec, actually. Let me go solve for some that will be different, and then we can test on those values instead of doing this guess and check. I don't think that's a good use of our time. So I'll be right back, and we'll have a better way forward. Okay. So it turns out that I was a little bit hasty in choosing American currency because the greedy algorithm will actually solve it correctly. And that's just because of the way these currencies are designed. So we are going to make our own currency. And we're going to use, what were the suggestions they used? 1, 3, and 4 are probably, yeah. So I'm looking at the Wikipedia article for this problem. And so what we're going to do is we are going to actually take the suggested denominations they use, which is 1, 3, and 4 cents. And we will call it a 1, 3, and a 4. Very clever naming we have. So how this is going to work is we can actually see this happen at 6 because our greedy algorithm is going to pick the 4 first, and then it's going to pick 2 ones, which is 3 coins. But what happens if you use this is now the optimal solution is actually to use 2 3s instead. So that's what I would expect to see. I don't think there's any other changes required. Nope. So let's actually see if that works. So we should be looking at 6. So yeah, you can see at our default of 6, we use a 4 and 2 1s. Whereas for our dynamic solution, we're actually using 2 3s, which gets us 2 coins instead of the 3 from our greedy solution, which makes this a better solution. It gets us the optimal result compared to our greedy algorithm, which is good. It means what we wrote is working. And you can see there's a few others that are actually showing this as well. So I hope that wasn't too meandering, and I hope you guys were able to follow it. But I think this is hopefully an introduction to dynamic programming. The idea is start at the top or start at the beginning and then work your way towards the end instead of figuring out a result and then trying to get back from that to your origin. And so there's a bunch of other problems like the Towers of Hanoi, I think, is a classic example, and that's the stacked disks where you can't have a bigger one on top of a smaller one, and you try to move them from one side to the other side. So you can also solve that problem with dynamic programming. But we did this, and if you guys liked it, let me know in the comments. If you want me to do more like this, let me know about that as well. Right now, I'm kind of just fishing for things you guys are interested in. And so if something sticks and you're like, I want more of that, let me know, and I'll do my best to make more. If this isn't something you guys want, obviously let me know about that as well, so I can focus on stuff that is more interesting to you. And yeah, I think that's it. So, till next time, see you, Internet.